All right, welcome back to the weekend. Are there any questions about postulates, quantum channels, states? Tristan raised a question that I'll address now. So the question was a completely reasonable question and something that was a critical oversight. So the question was, what is the difference between a coherent superposition and a convex mixture, right? Like last time we talked about how the set of quantum states, density operators, is a convex set, right? So what does that mean? Like if rho and sigma are density operators, then so is this convex mixture. This is a classical probabilistic mixture. If I say classical, it might be confusing, but it's a probabilistic mixture of two possibilities, right? And when you look at this and you've taken a math course, you might say, oh, that's a linear superposition, right? But in quantum information, we don't say that, even though it's mathematically correct, because of the interpretation that this is indeed a probabilistic mixture. And when we talked about the context of quantum channels, justifying that they're linear, we talked about experiments and how, like, I could be preparing rho or sigma probabilistically and not telling you. Okay, so this probability mixture is due to your lack of knowledge about which state was prepared, and that is very distinct from a coherent superposition. So let's talk about the difference. I think some of you know this from your quantum mechanics course, but typically you talk about a state vector, right? In a traditional quantum mechanics course, at least at the undergraduate level, you don't get into density operators typically, right? And so that's the key distinction. I should say that the density operators allow us to capture both these probabilistic mixtures and these coherent superpositions into one formalism. Okay, this was invented by von Neumann also. Okay, so the difference between a coherent superposition and a probabilistic mixture. So to talk about a coherent superposition, I will use state vectors, and then we'll write down the density operator corresponding to a coherent superposition. Okay, so state vector, this is the most common way that we'll write a qubit. Psi, this is a qubit state vector. Complex coefficients, alpha 0 plus beta 1. These are orthogonal states. They're the eigenstates of the sigma z, the z Pauli observable. Okay. We also call them the standard basis, and this condition has to be satisfied. What is the density operator? The density operator is the projection, the rank 1 projection onto the state vector. Okay, so it's an outer product, the ket with the bra. So when you write it down, you have alpha 0 plus beta 1, alpha star 0 plus beta star 1. And then you work this out, 4 terms. And if we write a matrix representation in the standard basis, it would look like this. Star beta alpha star. What are the conditions? We said a quantum state is a positive semi-definite operator with trace equal to 1. Because it's a rank 1 projection, it's automatically positive semi-definite. Okay? So then we have to check the trace condition. But guess what? The trace condition is consistent with this, which is also related to the probabilistic interpretation of quantum mechanics, often called the Born rule, or one instantiation of the Born rule. Okay, so what do you notice here with the density operator? You notice the presence of off-diagonal terms. So you have these two off-diagonal terms. What is an example of a convex mixture? So I want to show a distinction between a coherent superposition and a probabilistic mixture. So an example of a probabilistic mixture is this. With probability alpha squared is 0, probability beta squared 1. Okay. And then as a density operator, it would look like this. Okay. What do you notice here? No off-diagonal terms. What is the interpretation of this? The interpretation is that, I'm in the background and I'm an experimentalist or whatever. And with probability alpha squared, I'm preparing 0. Probability beta squared, I'm preparing 1. And I hand it to you. And I don't tell you which one I prepared. Your state is then described by this density operator. Okay. What is the interpretation here? This is a rank 1 density operator. A rank 1 density operator is an extreme point in the convex set of density operators. That means it cannot be written as a probabilistic mixture of any two distinct states, of any two distinct terms, right? So the interpretation here is that in the background, I am definitely preparing psi and no other possibility. I'm handing that to you. That's the interpretation of it, right? Okay, there's a question of, is this physically distinct from this? Indeed, the answer is yes, right? So are these physically distinct? Yes. Right? How do you measure what is an observable you can measure that would show the difference? What if you measure the observable sigma z? Will you see a difference in the expectation of this observable if you measure it on this state or this state? So let's do that calculation, right? Then we'll see. This is sigma z. It's diagonal in this basis. What is the expectation of this observable? Let's call this state rho. Okay. So what if we do trace z psi? When you do that calculation, first of all, the hint that you see is that this is diagonal in the standard basis. So in fact, it will only pick off the diagonal terms. Okay. And you'll get alpha squared minus beta squared. And if you measure this observable on this state, you'll get the same thing. So this is the wrong observable to measure to see a difference. right? What is an observable you could measure? Yeah, basically anything besides this, right? So indeed, X or Y would show the difference. And then, X would give a difference. Demonstrate difference. Okay, so that's all I wanted to say about that. But it's a very good point, and indeed, in my job talk here 8 years ago, it's like one of the first things I said on slide 2. It's that important. So it didn't make it out. Okay, but all right. Any questions about that? All right. So now I want to talk about an operation that is extremely relevant for quantum mechanics and quantum information. It is the quantum generalization of marginalization of a probability distribution. Right. So like if you have a joint probability distribution, random variable X and random variable Y, they have a joint distribution, right? Described by this. And then marginalization. Suppose I'm only interested. Suppose Alice has X, Bob has Y, and then Bob doesn't have access to Alice's system or whatever, a classical die or whatever it is, right? So we want to know what is Bob's distribution. What can you expect to see on his end through repeated experiments? To figure that out, we do marginalization of a probability distribution. So I think we said Alice was X, Bob was Y. We want to see Bob. So we do this. That's, and then we get the distribution that we call this. And if you want to be a little more, a little less abusive with notation, you would put the random variable that the distribution is identified with. Okay. So that's, you can call this classical partial trace. Okay. So now we want to know what is the quantum generalization. So partial trace. Let's begin by reviewing what is the usual trace. So if you have an operator X, we write trace of X. To be this operator. So you take an arbitrary orthonormal basis, you represent the operator in that basis, and then sum the diagonal elements. That's the usual trace. Partial trace is a generalization. And then, we thought of the usual trace as just like summing the elements of a probability distribution to be a legitimate probability distribution. That's what we want. We just put this in the washing machine. It must have got all messed up. All right, I'll just forget it. Okay, so given a bipartite operator acting on a tensor product Hilbert space, HA tensor HB, partial trace over B is this operation. So we can denote the reduced operator, similar to how we denoted the reduced distribution with PY, we'll denote the reduced operator with just XA. And then like B's gone. So this is defined, this is like a shorthand for the partial trace over B of XAB. So that's the notation that we use. We're about to define. Formally, you can think of it as the identity A tensored with the trace map on B acting on XAB. Okay. So formally, last time we took we talked about complete positivity, right? To define complete positivity, we took a super operator and we tensored it with the identity map. We formally defined what that meant. So from that, you could deduce what it is, but I will just tell you what it is at this point. So we're taking these elements, which constitute like a map that is a kind of super operator. In fact, this is a channel. You're tensoring each of those elements with an identity matrix. Right? And then you're doing the same over here. Okay. So you look at this and you might wonder, all right, well, gee, what does this mean precisely? Right? What does it mean precisely mathematically? What kind of matrix is this? This is a rectangular matrix. Right? This one's square. This one's a row vector. You tensor a row vector with a square matrix, you get a rectangular matrix. What is it? So let's expand on what this means. It's really this. There's the identity matrix. And then you're tensoring with a row vector. There's a 1 in the jth spot. Yeah, I didn't specify the notation. I guess like throughout the book, we always do this. So with this, there's a 1 in the j plus 1 slot. Okay. Okay, so that is a rectangular matrix. So you know how to do the tensor product, right? Okay, so that's what that means. And just for total clarity, you get this is a dA by dA dB matrix. Remember that XAB is a dA dB by dA dB matrix. Okay, so the point is that they match up. Right? The matrix multiplication, things have to match up. So this matches up with this. Okay. Similarly, what is the meaning of YAJ? Well, similar kind of thing. Now, there's a 1 here, J plus 1, so on. Okay. And this is a dA dB dA matrix. So this matches up with this, right? This dimension matches up with this dimension. And then what you're left with at the end of the process is a dA by dA matrix. And everything's consistent. Okay. This we use a lot, right? Because we're often thinking about, Alice is over here, Bob is over here. They have a joint state. Only Alice does a measurement. And so to figure out the outcome of the measurement, all you need is Alice's local reduced density. So that's the reason that we use it. And to make that concrete, and that actually motivates another way of thinking about partial trace. Like if you have some observable that Alice is measuring, well, MA, that could be an observable or a measurement operator. Both are actually falling in the class of observables. And this is done in the joint density operator. Then we're interested in what is the outcome or probability whatever, if we want a statement of the global picture being consistent with the local picture, and that's what partial trace does. So, yeah, and then where row A is equal to trace of B, row A. This is actually another way to define partial trace. Okay. That's a different way of thinking about it. That's the partial trace is the unique operator here, such that this equation is satisfied for all observables now. Okay. That's something that can be proved. I won't go into it. But that's another way of thinking about it. So maybe I'll interject with another observation. We're talking about semi-definite programs and maps and adjoints of maps, right? And like to figure out a semi-definite program, we boiled it down in this class to just like to figure out the dual of an STP, you have to figure out the adjoints. So, partial trace is a channel. Throwing away something is a legitimate physical operation. That's a channel. So there's a question of what is the adjoint of the partial trace. This equation shows you that. What is the adjoint of partial trace? Well, so formally the adjoint is defined like this. There's a super operator that acts on X, and then there's an output space that's compatible with Y. And you take the trace. And the adjoint is the unique super operator such that this equation is satisfied for all X and Y. Right? So now let's suppose that the map is the partial trace. We're going to pick phi to be the partial trace. And we'll write XAB. XAB will play the role of X, and trace over B will play the role of phi. Okay. It would be a YAB. So what do you see from this equation? That, well, this is satisfied. We can just substitute for row AB, XAB. Right? And then this right here is analogous to what we wrote right here. But then we see, oh, this equation is satisfied. So that's something you should prove as an exercise, I think. But what we find is that this equation is satisfied. Well, what's happening right here? This is playing the role of phi dagger. Now we have the full X over here, right? And so we can say, oh, well, phi dagger in this case, YA is tensor YA with identity on B. Okay? That is a legitimate superoperator. Okay? It's a legitimate superoperator. And so when you're solving STPs, and I believe some of the exercises, randomly you might get faced with this, right? In the homework exercises. So this is a useful thing to know that's not so obvious, right? And it tends to get used a lot. Okay, so there's that point. I want to make a separate point about related to how so many things are channels, and essentially every physical evolution is a channel. Right? Suppose that we were to normalize this identity by the dimension of B, then it becomes a state, right? And so this could be interpreted as take an input and tensor the maximally mixed states. That's a legitimate channel, right? It's saying oh, Alice has a density operator, and then Bob comes along and says, okay, I have the density operator, maximum mixed state, and let's put our systems together, right? And then the joint state will be the original state of the house tensor with the maximal state. That's what's often called appending channel. Like you have a state, and then you append another state to it. It's a simple channel, but it comes up. And it's like, it's not totally obvious when you're first learning that that's a channel, right? Okay. One final remark about partial traits. So we'll do it up here. This is another way of defining it. Okay, there are different ways of defining it. So if you take orthonormal basis of operators for A, it's ij, and then an orthonormal basis of operators for B, partial trace over B will act on this B system and contract. Will contract this operator to a scalar. Okay. And when you do that, you'll be left with ij on A and then lk. Okay. That's the contraction. Okay. And then that's the same as this. Right. So this is useful because an arbitrary operator XAB can be expanded in terms of ijkl, right? There's some coefficients x labeled by the indices ij, k, and l, and then you can expand in terms of this basis. Okay. And so if you wanted to take the partial trace of an arbitrary operator, you could expand it in this way. Use the fact that partial trace is linear. You can bring it inside the sum, inside these coefficients, and then contract them. Okay. Okay. Any questions about
So algebraically, you would write it like in the bottom left where we have that XA is that tensor product identity with you would set these instead of J's for this example, you use like M on the left and L on the right.
I would come up with a new index, M. Right. So let's work through that. We put M on B, then sum over M, right? Another thing that we'll eventually start doing is if an operator is not there, it's implicit as the identity. That happens a lot when you face the literature, right? It's just to make the notation more compact and easier to read. But when you first learn it, it can be confusing. So here, when I write XAB sandwiched by M on the left and M on the right and a sum, I mean this. The identity on A is implicit. So what you do then is you would put here M, and then the only term that would survive the sum would be when M is the same as L and K. But then that leads to precisely this.
Yeah, but for like an operator, like whenever you write trace in terms of like the tensor product, I can still write, like if I was doing a proof, is what I'm saying. I can use that form.
Any of these,
okay.
They're all equivalent, unless the exercise is to prove that they're equivalent. Okay. So, good. All right. So let's continue. I'm gonna. Okay, so the consequence of partial trace is that the marginals of a pure state have the same eigenvalue. Okay? And there are aspects of this that are unique to quantum information theory and quantum mechanics. And I'll point that out. Okay, so marginal states here state psi and b the same non-zero eigenvalues. To prove this, what should we try? What's the most important theorem that we know about pure bipartite states? Schmidt decomposition. Okay. So Schmidt decomposition. So proof is use the Schmidt. So starting point. So what is the Schmidt decomposition? Well, it's on the side. Remember that you expand this like this. Lambda k. So these are called the Schmidt coefficients. R is the Schmidt rank. And these are strictly positive. This is an orthonormal basis. This is an orthonormal basis. And they're coordinated in the superposition. So if we use that, well, then it becomes nice. So you kind of expand this out and use linearity. The two indices k take on. Now use linearity to trace, and then we can use what we just erased, right? So K Q prime onto R. Trace B. Okay. This is an orthonormal basis, so it collapses through a delta function. And then what are we left with? We're left with the reduced density operator in its diagonal form. All right, so these are the eigenvalues of the reduced state. You can do a very similar calculation. Trace over A. On B. So indeed, this is the diagonal form of the reduced density operator on B. And the eigenvalues match. So how is this unique to quantum? It's the whole thing together. right? So you have a joint state, decide this state right here is a definite state. And that's how we described it. It's a extreme point. It can't be written as a probabilistic mixture of other states. So classically, that would a definite state would be a definite bit string, for example, right? I would just pass you a sequence of bits, right? But what do we have here is this. What is the distinction? For this definite quantum state, the reduced states are mixed. You don't have that classically. If the joint state classically is definite, then the reduced states classically are definite also. You don't have these mixtures. Right? And there's a famous quote of Schrodinger, right? I'm trying to recall it. It's like, I would not call that one, but the characteristic trait of quantum mechanics, the one that separates its entire line of thought from classical thinking, something like that. That the joint state can be definite, but the reduced states can be indefinite. The quote goes something like that. It's very famous. So this is a very interesting and important observation. And here you have and the statement applies if R is greater than 1. If it's strictly greater than 1, right? If it's not greater than 1, then you're actually in a classical situation where there's no entanglement. This is just a tensor product state. Okay? So the distinction comes about when R is strictly greater than 1, which is how we defined an entangled state vector last time. Okay? So yes. This kind of thing gets used a lot. And there's another important clarification to make. And this actually needed to be made with Schmidt decomposition. Suppose I have a pure state of A, B, C, D, E. This is now, as we wrote it, a I don't know, what is the word? Yeah, 5-party state, right? So you can make the Schmidt decomposition and this whole line of reasoning apply by making a bipartite cut. So, okay. Charles says these systems and then these 4 together. And then you could do a Schmidt decomposition. All right, YK, K, and YK. When you first see that, it's quite surprising. You can do that. And the whole reasoning applies that we did here. Right? The reduced density operator on A would have the same eigenvalues as the reduced density operator on B, C, D, E. These states, phi K, they could be entangled states of B, C, D, E. Right? And then you could do kind of a recursive Schmidt decomposition. You could look at each of these and do a Schmidt decomposition for those. Right? So it's nothing prevents you from doing that, and that can be helpful in some situations. So the other point that I want to make is that you can make the bipartite cut anyway. Make it here, right? But then, the eigenvalues of the reduced state on AB, they will be the same as the eigenvalues of the reduced state on CDE, but not necessarily the same as the eigenvalues on A and B. Right? Not going to. So anyway, you can do this for any possible bipartite cut. There have been attempts to generalize Schmidt decomposition to more parties than a bipartite cut, but there's no, can't really do it. It's related to SVD of a tensor, of a rank 3 tensor. I think it exists, but it's not good notion. So the Schmidt decomposition really is a 2-party thing. Okay, let's move on to We talked about entangled state vectors and product state vectors. Now let's define entanglement in its most general form. So this, let's make it a little clearer. So a bipartite state is separable if there exists a probability distribution X and sets states such that, sorry, there's my state. Bipartite state sigma AB. So we can write a state like this. It's said to be, another word is unentangled. Not entangled. What is the meaning of this? A separable state is a probabilistic mixture of product states. The way you can think about this is these states, there's not any quantum interaction needed between Alice and Bob to prepare these states. They can be prepared by a third party in the background holding a classical variable, X, distributed according to this distribution. It's like I have this classical X, I'll then hand you, I transmit over a classical channel, X to you and to Roy. Send the classical X. And then you'd receive it, and then you'd say, okay, I'll prepare omega XA, and I'll prepare tau XB. And then you just like forget which X you received. And then that's the resultant state of your joint system. So that was a procedure. There's this classical thing in the background. The context of Bell experiments, that's called hidden variable. So this classical hidden variable background is underlying the process by which this is prepared. So the state is not separable. And it is entangled. Okay. So this is an example of something you could say easier said than done, right? It's easy to define this, but if I hand you the mathematical description of a row AB, it's the bipartite state, and I ask you, is it separable or entangled? That is actually a computationally difficult problem. It's been proven in a computer science, theoretical computer science tends to be NP1. Okay, and so there's not going to be a simple algorithm to decide. Whereas for state vectors, remember we had a simple procedure. We just do the Schmidt decomposition, and that amounted to doing a singular value decomposition, which you can do in time, polynomial, and the dimension states. So it kind of depends on your notion of efficiency. That's the precise statement. And, you know, the statement about deciding separability for mixed states is that if you follow like the standard belief in theoretical computer science, then you know, to decide whether a state's entangled or not, the best algorithm you can hope for would be exponential in the dimension. Yeah.
And if the system is continuous variable, so it's infinite dimensional.
Different story. Yeah. Good question. This computational problem is for yeah, it's framed strictly in the finite dimensional. The continuous variable problem, I think the question, I mean, there it's going to be hard in general because of this. However, you could be interested in a particular class of states, such as bosonic Gaussian. And for those, there are certain cases that are known. I believe, don't quote me, I believe the most general statement that's known is that if it's a Gaussian state where A is a single node and B is an arbitrary number of finite nodes, then it's easy to decide. It's some function of the covariance vector. So this discussion is somewhat out of scope. I did teach a course on Gaussian quantification back in 2019. There's a, if you're interested, there's a book of Alessio Serafini. You know it.
Yeah.
That one's the best one. It exists. Okay. Yeah.
I have a question. It's kind of just before this is about the Schmidt decomposition.
Right.
The fact that any bipartite cut has to have the same non-zero eigenvalues.
Yeah.
Is that the reason when you purify a state that's just as big as
Yes.
a state you purify?
Yeah.
So you have as many, at least as many eigenvalues.
That's right. We're going to get to that. Okay. Yeah. Yeah. The other thing to remember here is like, it's kind of surprising about pure states. Suppose that A is like a single qubit and B is a trillion qubits. Then, because A is limited to be no more than 2, the Schmidt rank cannot exceed, remember, I think we said this before, cannot exceed the minimum of the dimension of A and the dimension of B. So even if A is a single qubit and B is a trillion qubits, the Schmidt rank cannot be larger than 2. And so it's like this pure state, even though it's embedded in this huge Hilbert space, it's only occupying like an extremely small portion of it. That's an important thing to remember. Okay. The definitions. A pure state is maximally entangled with the Schmidt coefficients, right? These lambda k's, but they're uniform. Okay? The Schmidt coefficients are uniform. What does that mean? All equal to 1 over root d. So that means that, for a maximally entangled state, you can write it like this. 1 over root d a equals 1 to d. And then some orthonormal basis. Okay. So we talked about maximally mixed states. We gave a justification of why they're called maximally mixed. I don't know if you remember, we used purity and Renyi 2 entropy. You can do similar things. You can have quantifiers of entanglement. And there's a whole theory of entanglement, which is about coming up with ways to measure entanglement. We have a chapter in the book dedicated to that. So by all measures of entanglement that exist, the maximally entangled state has the largest amount of entanglement for a fixed dimension. So if you have a bipartite system where the minimum of A and B is equal to D, a maximally entangled state will have the largest amount of entanglement of that system, of those systems that's possible. And eventually we'll see how amazingly useful maximally entangled states are. I can rattle off 3 protocols where you see that they're used: teleportation, superdense coding, and quantum key distribution. We're going to talk about the first 2. We're not really going to get into the last. Okay. I wanted to find some things. Bell states. It's a set of maximally entangled states. Another point to emphasize is that there's not a unique maximally entangled state. Right? These could be arbitrary orthonormal bases, and all of them are maximally entangled according to an entanglement measure. The entanglement will be useful as long as Alice and Bob know these bases. They have to be able to manipulate the state. They have to know the bases. Okay, Bell states. These are famous, used in teleportation and dense coding. 4 of them. I'll write them out in front. This one right here is often called the standard or canonical maximum entangled state, where you fix these bases to be the standard bases of these systems, right? 0 and 1, and then you make the uniform superposition. So that's often the standard maximum entangled state. Y minus. Or minus. So this is also a maximally entangled state. In the definition, we had a sum. So you can think of the minus sign as just being assigned to the 1 state of one of these, right? And then your basis would be 0 and minus 1. And that's an orthonormal basis. Right? And so it fits the definition of a maximum entangled state after the like. Thank you. Okay. Sign plus. maybe I'll do a shorthand. Plus minus. Sets of those are defined. This is an orthonormal basis for a 2-qubit Hilbert space. And that means you can form a measurement out of it, right? Like what I'm saying is that, all right, let's make an abbreviation. This is a common abbreviation that we do. You might have already employed it. Instead of writing 5 plus twice, we just write it once. And this is a shorthand with a density operator corresponding to this. More generally, like we'll do this kind of shorthand. So the statement I was making is that 5 plus 5 minus psi plus psi minus is the identity of it. Each of these is a density operator that corresponds to a projection. So they're each positive semi-definite. And from this, it follows that this corresponds to a measurement. You know, there's a measurement. It's called the Bell measurement. It consists of these operators. And this Bell measurement is used both in superdense coding and teleportation. Why don't we actually just talk about superdense coding? That comes later, but then you can, this will be like the first protocol you'll see since we talked about Shannon, which was like a long time ago. There's a hurricane and all kinds of stuff for that. So let's just talk about superdense coding. To motivate superdense coding, we need to make another observation. The other observation that we need to make is that we can get phi minus by applying sigma z to the system A of 5 plus. We can get psi plus by applying x to 5 plus. And you can get psi minus, let's see, this one I was something to think about. Yeah, you do x and z. Right, so if you do x, you'll get psi plus, right? And then if you do z, the 1 is there, and it'll flip the 1 with a minus sign. Is this clear? So this is the key observation of superdense coding. Right? So what does superdense coding look like? This is like a quantum circuit diagram that we can use to talk about the protocol. Here's the lab of Alice. Here's the lab of Bob. And we assume that the protocol begins with them sharing the standard maximum entangled state, 5 plus. So in this, they need to know like their reference frame. You need to know like the basis that's there to be able to manipulate it properly. So that's kind of assumed. And then the goal of the protocol is for Alice to send classical information to Bob. Right? So Alice wants to send a bit called little x, and also a bit little z. A bit is 0 or 1. This is 0 or 1. So what's happening here is by doing, this is a key observation. By doing a local observation, by doing a local operation, Alice can rotate the global state to be different from what it originally was. Right? The initial global state corresponds to this 5 plus, that's the density operator. Then, this notation means if x is 0, Alice does identity. If x is 1, she applies x, big X. That's what the notation means. Same here. Okay. And so then, you think about the possibilities, right? So make a truth table. X, if xz is 0, 0, the global state stays as 5 plus. If xz is 0, 1, the global state becomes 5 minus. If it's 1, 0, the global state becomes psi plus. If it's 1, 1, the global state becomes psi minus. Okay? So it's an orthonormal basis. Alice can then send this qubit for share over a qubit channel. We'll assume it's a perfect qubit channel. Okay. And Bob receives it. He then does the Bell measurement. So that's how we depict measurements. It's not like a frown or a smile. It's like a measurement dial. And the Bell measurement corresponds to this. So this is an orthonormal basis. The state here is encoded in that orthonormal basis. So Bob will deterministically figure out which bits Alice sent. Right? So those are calculations you can do. And Bob can perfectly decode X and Z with 2 classical outputs there. The double wires indicate classical information. So that's the protocol. So we can summarize it as consuming I'm going to introduce this word e-bits for entangled bits. That's the same as a Bell state, but it's a communication resource, right? Anything that crosses the dotted line separating Alice and Bob's lab is a communication resource. So we assume at the beginning that they share a Bell state. That's when it becomes a shared Bell state between distant parties, then we call it e-bits, because it's like a communication resource. So consuming an e-bit and a qubit channel, a perfect qubit channel, right? It's just like an identity channel that goes from here to here. Alice can send 2 bits. That's super insulated. Right? And we can make various other statements. Suppose there were at this time in the protocol, before the qubit has been sent. What is Bob's reduced state here? That's a calculation you can do, and you'll find each of these 4 possibilities The reduced state here is the maximally mixed state, identity over 2. So the reduced state, like if you do a partial trace of the density operators formed from these state vectors over system A, you'll find for each of these possibilities, the reduced state is maximally mixed. What does that tell you? That if Bob does a measurement on this qubit alone, he will not figure out anything about the classical message. Because the reduced state here is the same for all of them, independent of the classical message. By the same reasoning, if there's an eavesdropper tapping the line here, and the eavesdropper does not have access to this system, the eavesdropper will not be able to figure out the classical data being transmitted. It is only with both qubits that Bob can decode. Okay. Let's supernet's code. That was discovered in 1992 by Charlie Bennett and Stephen Wiesner. Stephen Wiesner sadly recently passed away. That was one of the main things that he did, and then he decided to live the rest of his life in peace on a farm. So, might be nice. Stress free. I'm sure the farm has its own stresses. Okay. Anyway, all right, we have about 10 minutes. Keep going. Any questions about supernet's code? It's like a core quantum information protocol. We can motivate future topics. You could say, oh, well, here you assumed the EBIT was perfect. You assumed the channel was perfect. In reality, they're not. What do we do then? That motivates quantum Shannon theory. The kind of things that Shannon thought about. Like, oh, if there's a noisy channel, how many bits can we transmit over it? And so we can, start at least wondering about these possibilities. And the goal, maybe in a month and a half, is to start getting to that kind of stuff. Right?
Besides that, Simon, when the two reduced states, they are entangled, but in a different lab. So depending on the distance, that will affect the attachment also, right? They are not going to stay attachment for.
Oh yeah, in practice, yeah, and that's like having a noisy channel, right? Like, in practice, when you send this over, even in free space, that there will be loss, right? And so you'll have to combat that. And the same here when this gets distributed, right? It won't be distributed perfectly. And so that's been a topic of research in the past, but it's ongoing. I was trying to make the technology, people are trying to get technologies more practical. Okay. We can generalize the Bell states to, this was for qubits, we can generalize them to qudits, d-dimensional systems. Okay. And we generalize them, we use what's called Heisenberg-Wilde operator. These are one generalization of the Pauli operators to qudits. And you'll see these a lot in the quantum information literature. So we use W for them, and they're indexed by X and Z. So Z, big Z of little z, is defined like this. So the Z operator is diagonal in the standard basis. This represents the generalization of Pauli Z. Right? If D is 2, this reduces to Pauli Z. This will leave a check. And then this one will be a generalization of Pauli X. So it will be a shift operator. Addition is modulo D. Right? Sometimes you put a circle on the plus to indicate that. Okay, so what are the qudit val states? You take the, so we'll define them as phi sub zx. Zx tensor I, and then acting on the canonical maximally entangled state vector. So phi d this is the canonical maximally entangled state, MES maximally entangled state. Okay. So these are all things I'm not going to go into detail, but just say that they're true, and some of them are likely exercises in the book. If they generalize the Bell states, we said a number of facts about the Bell states. One of which is that they form an orthonormal set. Okay. So that's true for these. This is an orthonormal basis. So they also form a measurement when you take their projections. When you take the density operators of them, you form a measurement. And indeed, this whole picture applies. This picture for superdense coding, it gets generalized to qudits. Right? It applies fairly immediately. Change of notation is this. X goes from 0 to d minus 1. Z goes from 0 to d minus 1. I'm just going to put this. Then the picture applies. So what does it say? They start with the canonically maximum entangled state vector. Right? Then the value of x and z. The order, yes, the order is correct. Right? X and z. Depending on this value here, Alice applies x of little x, which is encoding one of d values, and then z of z, one of z values. I'm sorry, one of d values. So overall, d squared classical values encoded into the state. this is now a qudit, this is a qudit, sends over a qudit channel, does the bell measurement in the qudit bell basis and figure out X and Z. Same protocol. Just using the fact that it's an orthogonal basis and each of these are unitary. They correspond to physical operations that Alice can do locally. That's qudit, so that's good. And then the same statement applies. Assuming an edit, a d-dimensional entangled state, and a qudit channel, Alice can send two dits. That might sound funny, but you can read that in the literature. So we could also say d squared messages, one of d squared messages. And that's qudit super coding. All right, we pretty much hit the time. There's 2 minutes left. We need more time to introduce this concept. Any questions? So we'll call it a day. See you Wednesday. There are office hours today if you have questions. Will anyone come to the office hours? Good. All right. Yeah,
Could I ask a question like right now, because I can't make office hours?
it's fine. Yeah.